Good afternoon and welcome back to the second session of today's program. Hope you enjoyed your break. In this session, there will be 5 contributed talks. Chairperson for this session will be Dr. Raju Hazari. Dr. Hazari received his graduation, post-graduation and PhD degree from IIST Shibpur. He is currently working as an assistant professor at the Department of Computer Science and Engineering, NIT Calicut. His areas of research interest are theory and applications of cellular automata, machine learning, cryptography, and security. I'd request Dr. Hazari to come on dais. Over to you, sir.
Thank you, Tanushree. So, welcome to the third technical presentation session. In this session, 5 papers will be presented by the authors. Most of the papers are actually given as a project work during the last summer school 2022, and there's so many actually work have they submitted in this conference. Few are actually accepted. So I would like to invite the first speaker of this session, Subrata, and the title of this work is Modeling Spread of Contagious Disease by Temporally Stochastic Cellular Automata.
Good afternoon, everyone. Myself, Subrata, I am presenting my one of summer school project, that is modeling of spread of contiguous diseases by temporary stochastic cellular automata. Before going to the introduction, I know we all are facing a tremendous, deadly situation in previous some years due to some COVID-19. So not only COVID-19, there are more than one various type of dangerous virus or some diseases, that is SARS, H1N1, MERS, etc. This is very deadly and the spread was very high and the death rate was also very high. That is a very dangerous situation for all over the world. So this scenario indicates the necessity of developing the mathematical and computational models and that investigate the spread of this type of virus. So this is very obvious to all of us to model some kind of technique that we overcome all of this situation and manage the situation if in the future we can face this type of virus impact. So the required of developing model is to forecast the spread of in future, and the second thing is in future we have to prepare to sufficient management to face all of these diseases. And we have chosen that cellular automata as a backbone of our model because the cellular automata provides our global framework where the rules and the states and neighborhood structure are tuned to implement the parallel complex dynamical systems. So our proposed model, before going to our proposed model, the basic characteristics that have in just such kind of viruses is the locality of transmissions and the chain of infections. And third one is a high rate of spread that makes the virus very deadly. And the fourth one is the some external factors that we have taken to resist the spread of that kind of viruses, that is quarantine, vaccinating people, etc. And the fourth one, that makes the virus more deadly, that is a mutation. We all know that the various waves we have to face. The first wave, the death rate was quite low, but in case of second and third, that death rate is very high, because due to the mutation of the virus. And we are trying to incorporating this type of features into our CA. In our traditional CA, we most of us are CA people, so we know that this three property is the is quite obvious in a traditional CA, that is the locality of transmission, chain of infection, and high rate of spread. That is, locality of transmission means a CA changes states based on their neighbors, and the chain of infection means every cell, impact of every cells spread or propagate through all of the lattice. And the third one is a high rate of spread. It's depend on the information flow of the rule quality. So these three is quite obvious in the traditional CA. Somehow the second factor is most interesting, that is the external factor, that we are quarantined some of the places. We have to model and deviate from the traditional concept to some extent, that we provide some partial blocking information, and somehow we resist to spread the virus, I mean spread the information flow in the lattice. And the most important one is the mutation. Somehow we give some flavor of mutate our rule at different time step, so that it can mimic the actual scenario of our environment. In this way, I mean in this direction, we deviate the traditional CA, and we get some flavor of, in a previous work, that is temporally stochastic cellular automata, where instead of using single rule, we have some flavor of that another rule act as a noise to perturbate the traditional system. So in that case, we can assume in this way that a system follows a general rule, which is a traditional CA, but somehow another rule is impact with some probability, so that all the traditional scenario is perturbed. In this direction, and another important features we need to introduce, that is the distance neighbors. There is no concept of distance neighbor in traditional CA. Somehow, if some people traveled from another region and carried out some infection or disease, we all know in this way the virus spread over India. So in this giving this flavor, we have introduced some concept of distance neighbor, and we follow the Moore neighborhood model, that is 8 neighbor and itself states and more, I mean updates based on that eight neighbors and itself. But somehow we are considering that instead of 9, we are considering the 10 neighborhood, and the last one is the distance neighbor. Here the star indicate the distance neighbor, and others as the normally Moore neighborhood structure. So the key ingredient is we follow that the F rule is a indicate, I mean the one rule is a default rule which indicates the virus spread, that means the infection spread, and the second rule indicate the immunity, that is applied with some probability obviously. So we consider, and at this moment the one is F and one is G. It consumes like a normal temporary stochastic CA, but our model is far deviate from normal temporary stochastic CA. That is, we named it as a non-uniform temporally stochastic elementary cellular automata. That is, we use a set of TSCAs, that is for the first time, for the first some iterations, this F and G and T, this is the norms of TSCA. First for first few iterations it follows this, and after that it follows this, and in this way we somehow mutate the virus. If the first one is a F1, considering that is the spreading power is somehow let's say the spreading power is 100. In the second iteration the virus mutates and it gets 200. In this way we evolve the model. Now we need to consider also partial blocking. To go for the partial blocking, we need to know about the information flow based on the k equivalent neighbors. That means for some neighborhood how much it depends, I mean how much it can impact the self state. that is calculated by the k. K indicate the epsilon, k indicate the neighborhood, kth neighborhood that impact to the changes of states. So here 10 neighborhood is there. So for every neighborhood, we are considering every direction of information flow, and that is a set of parameters which impact to that neighborhood. This is the formal calculation of calculating rules of calculating information flow. I'm not discussing this. This scenario indicates the partial blocking. This region is a partial. We say it partial block because it is not the fixed block. It may vary. It may sinking gradually over the time. We all know that in real time scenario we some quarantine some of the places, and when the impact of the virus get reduced, then the quarantine we omit the quarantine place, or we shrink the quarantine place in such a way that it is after some time there is no quarantine in there, all is open. In this way, I mean, that's why we are called as a partial blocking. The blocking is get reduced over the time. Here the reduction of the partial blocking is depends on obviously the all of the neighbors. If the neighbor of I mean, if we consider that this direction, if we change 0 to 1, then if the output state, I mean current state is changed, then the partial block that implies that there are some sensitive issue, that when we change gates from 0 state to 1 state, there is some changes in the current state. So in this way we calculate all of the direction information, and based on the information flow we have selected some partial block. We will see it in the simulation how the partial block occurs. So here many of one viruses we have discussed. I mean, we have named one of that is the most popular COVID-19, we all know. So I am actually working on the COVID-19 especially as a case study, and we develop, I mean, we build some tradition model, I mean simulation model, that we take first one is a F1G1, and with some probability that is 0 probability for the 30 iteration. In this way we have taken 1 2 3 4 5 type of TSCA over the time. First one apply for 30 iteration, second one is a 50 iteration. It is based on some experimental issues to match the real time scenario. So this is the rules we have applied for F1. We have considered, if we considered the two state, if a cell consists of two states 0 and 1, one is considering as a infected and 0 in considering as a immune. So always if we can say that, I mean we said I said previously that if F is a infection rate, so as if F is an infection rate, so always F tends to all zeros to 1. So that's why it gets to 1 with some probability. For the same time the G tends to 0 with some probability. In this way we are mapping the immunity and the spreading rate. This is the information flow of all the rules we have calculated. See, there is a much of bit low information flow and the high information flow. There is a lot of low information flow. For this reason there is a partial blocking occurs in the several places. So first one is this is a simulation picture. A is a starting point. We have considering this is a lattice, and lattice is considering, if we consider it is a scenario of India, and every cell is depicts as a place of India. So it is starts from a single black is the infected cell. After some time of iteration it gets some of the black, I mean a lot of the blacks and lot of the whites. That means this is the infection and this is the immune region, and this is the partial block region where the infection could not flow because of that information flow and the rule, etc. So at this time it picks the highest highest infected counts, and for gradually after B to C the infection is degraded. That is it indicates that from starting it shows the first wave, and it get back to the some immune cells, lot of immune cells, and then again it goes to the second wave. There is a lot of black cells. So this is a graph I have calculated. It is nothing but a count of black cells and white cells. That means count of infected cells and count of immune cell. This is an infected cell. This is a graph of infected cells, and this is a graph of immune cell. We we have merged both of the two graphs, and we got that that wave type scenario. That is, if we consider this is a first wave, if we consider this is a second wave, this is the nothing but the mapping of real time scenario. And we have got the real time data from the Kaggle website. And if we map these two data, this is a real time data and this is our simulation data, simulated data, so it is quite similar. It looks quite similar, and the wave is exactly same. Another thing is, we all know that there is a third wave as well, but at that time, as this is a Rajuda mentioned, this is a summer school work. At that time I have got only the second wave data. That's why up to this we have developed the up to second wave, it is mapped, similar to map. So this is quite interesting, and further, if we got some data, we can extend this work to map another, we build another NTCA model. So this is a end of the slides. So this is a discussion. We choose the CA as a natural choice, and spread of which can simulate in using this model any kind of highly contagious virus, because when there is a virus, there is some immunity and spread collision. So we can provide the number of you can provide to build the number of cells at a time, how much it gets to immune, how much it gets to spread. In this way we can get the model, and we can get the TSCA. We can build it based on the probability, how it can immune, how it can get infected. In this way we can model any of the viruses based on these settings. And second one is that the distance neighbor is most interesting. As we all know nowadays, the distance neighbor is the main reason, or main reason to spread a virus from a certain region to all over the world. Third one is the applied of TSCA rules have varied in time, indicates the various of spread of different situation, and it also indicates the mutation of the virus. Our future direction is this is only the second wave data of COVID-19. Our future direction is to mimic all types of data, like all types of diseases like HIV, influenza, H1N1, etc. And we can also mimic, apart from the disease, we can also mimic any kind of situation where two things is reliable of each other or dependence of each other. This is an acknowledgement we acknowledge to Professor Shukanto Das and Dr. Shovik Roy for giving comments and suggestion on this work during the Indian Summer School on Cellular Automata 2022. This is some reference. Thank you.
Okay, so Subrata, I have one questions that you designed some stochastic CA rules to simulate the COVID-19 behaviors, correct? How to spread the COVID-19. So do you think this same kind of stochastic CA is behave like other pandemics or maybe other kind of disease? Have you checked with these things?
No, I have not checked it, but if you consider any kind of disease, there is some of spreading and immune system is there. Always when a disease gets spread, all our doctors or etc., all our hospitals, they are ready to build some medicine or etc. So they are fighting for get how we get immune based on overcome of that situation. So in our model, there is always at any time there is a two situation. One is the spreading, one is the immune. So always we can if you consider this is a parameter, that AFG and tau, and the during some during over the time, if we can able to change this parameter as a this is a norms of our model, then we can mimic every kind of virus or disease, I think so. But I have not checked. I have checked only the COVID-19 situation.
So just you mentioned that two parameters you consider, that F and G, that is one is for immunity, one is for the spread. So do you think how these two parameter is like relate, like any particular relation you build, like if F is like behave like this, like immunity system is this much and then spread is like this much, is there any relation you find?
Yes, actually there should be some relation obviously, but our work is based on only experimental. There is no theoretical relationship over there. Obviously there should be some theoretical relationship, but we need to explore more about it.
Okay, thank you.
Excuse me, but nothing is audible to me. In case if you are speaking something, and if in case someone can hear me, nothing is audible to me. It's audible now. Sir, whatever you are saying is not audible to me. Should I present my slides?
Okay. Yeah, you can start.
Thank you. So, hope my screen is visible to you all. Can someone please confirm that I'm clearly audible and visible? Can I get confirmation from the audience? Can someone please confirm? So I'm not sure whether I am audible or not, or whether my screen is completely visible or not. Can someone please confirm?
Yes, you are audible.
All right, thank you. Thank you so much. All right, so the title of the paper is Genealogy, Interceded, Phenotypic Analysis, GIPA of the ECA rules. And this study demonstrates a different classification of 88 minimal representatives of the ECA rules using the information theoretic measures. And in this study, it is proposed to use the entropy time diagrams to compare the ECA's behavior. And how do we draw the entropy time diagram? So basically, we need to compute the approximate information content of a configuration as the time evolves. And so basically, we are computing the entropy of a configuration. And the purpose of computing the entropy of a configuration is to know the level of the orderedness and the disorderedness present in the configuration. So therefore, we take the help of the concept of the bientropy to compute the approximate information content of a configuration. And the meaning of the term, the level of the orderedness or the disorderedness will become clear through this table. So like in the first case, say if we assume that this is the configuration, so this is perfectly ordered. We find all ones here. And same is the situation with the second example, with the second string, wherein this is also perfectly ordered because here again we have all zeros. So therefore, the information content of these two configuration is pretty low. Say it is 0. However, if you consider the third case, so in the third case, we have almost equal number of the zeros and the equal number of the ones here. But this is also mostly ordered because mostly we do find the occurrence of the 0 ones here. And so similarly, with in the next examples also, we observed some kind of the regularity. So therefore, we want to capture this level of the orderedness and the disorderedness present in the different configurations. So therefore, instead of using the Shannon's entropy, we are using the bientropy, and which was proposed by the Grenville-Kroll, and this is the formula to compute the bientropy of a binary string. And now, so the meaning of the entropy time diagram is, so we apply the bientropy function phi, and we repeatedly apply it over the different configurations as the time evolves. So assume that C is the initial configuration and G is the global function. So we repeatedly apply the bientropy function, thereby converting the space-time diagram like this into an entropy time diagram. So in this figure, this is the entropy time diagram for the rule 105, and with the value of n, number of cells is equal to 16. So in this way, we draw the entropy time diagram, and which is crucial. So basically, while classifying the rules, we compare the entropy time diagrams. So as far as a summary of the different CA classifications reported in the literature is concerned, a comprehensive review of such classifications is given in a short research note by Martinez. And Wispol et al. Has given an intuitive categorization of the CA classification. So by and large, most of the classifications reported in the literature are categorized into two categories. So either they are based on the CA's rules table, basically they are based on genotype, or they are based on the generated space-time pattern. So they are phenotypic. So in this study, we use both. So therefore, the title of the study is genotype interceded phenotypic classification. So we use both. And the genotype of an ECA rule is perceived as the amount of the information processed, and it is captured through four measures. So we have proposed four measures to capture the internal of an ECA rule, to capture the genotype of an ECA rule: diff entropy, DE, and similarity configuration ordered, basically. So the parameter SCO, and similarity configuration immediate, so therefore SCI, and similarity configurations fluctuations, so the name of the metric is SCF. So we propose four metrics to capture the genotype of an ECA rule. And then by clustering the temporal sequences of the entropy values of the different rules by using the dynamic time warping method. So thus the combining both a genealogy interceded phenotypic analysis of the 88 rules is proposed. So these are the proposed measures. So what happens? So this dynamic time warping is a popular technique to cluster the time series data, and I shall explain this in the coming slides. So here the explanations of the proposed measures goes here. So diff entropy is the maximum absolute difference in the bientropy values of any reachable configuration from the initial configuration. And this parameter basically captures the impact of the transformation carried out by a rule. And the second measure, similarity configuration ordered, counts the similar bientropy values of the two configuration in a sorted list of the entropy values with a threshold of 0.01. And this parameter captures the frequency of the similar reachable configuration. How many times similar configurations have been reached by an ECA rule. And the third metric here is the same configuration immediate. It counts the similar bientropy values of two successive configuration and with a threshold of 0.01. So this parameter captures the frequency of the successive similar reachable configurations. So how basically through this metric, we are measuring that how many times the information content of the two immediate configurations remain the same. And the last metric here is the similarity configuration fluctuation, which counts the fluctuations in the bientropy values. And we only take those fluctuations into the consideration whose value is greater than the half of the DE value, half of the value of the first metric, difference in the entropy values, with a threshold of 0.01. And the dynamic time warping is a method to calculate an optimal match between the two temporal sequences and which do not sync up completely. So basically, since we have to compare the two entropy time diagrams. So therefore, this technique is quite apt to compare them. And here this pi is the alignment path between the aligned time series data points, and this is quite a popular technique and which is being widely used in speech recognition, stock markets, predictive analytics, etc. So how do we carry out the classification of the ECA rules? So let us consider, say, two ECA rules, say S and S prime, and having the global functions as GA and GB. So initially, by repeatedly applying the bientropy function, we construct the entropy time diagrams corresponding to S, and then the entropy time diagrams corresponding to S prime. And then we compute the value of the DTW in between S and S prime, and say if this value is greater than epsilon. So we only take, we consider two rules, S and S prime, related only if the value of epsilon is less than 0.5. The value of epsilon here in this definition lies in between 0 and 0.5. And if the value of the epsilon is 0, then this is the case of the strong association in between, the strong similarity in between the two rules S and S prime. And if the value of the epsilon comes out to be greater than, say, 0.5, then no similarity exists in between the rules. So here we define the level of associations. So strong means that the value of all the four measurements, DE, SCO, SCI, and SCF are same with the zero value of the DTW. So this is quite a rigid constraint to qualify two rules as strongly associated, strongly related, that the value of all the four measurements remains the same with the zero value of the DTW. And the level of the association would be moderate if the values of all the four measurements are similar. There could be a slight deviation, but with the zero value of the DTW. And it endorses a similar transformation. So if there exists a moderate level of the association, then clearly there exists an association relation in between the rules, and it endorses a similar transformation, information content wise, carried out by those two rules, and highlights the effective use of the proposed approach, wherein the space-time diagrams of the rule may differ. Because here we are focusing on the information content, so quite possible that the visual appearances may differ, however, their information content may remain the same. The level of the association would be weak if the values of all the four measurements have slight differences, but then the value of the DTW remains less than 0.5. I would like to emphasize this thing again, that if the value of the DTW parameter is greater than 0.5, then no association exists in between those two rules. So the simulation setup is like this, that we considered the 88 minimal representatives of the ECA rules, and we analyzed entropy time diagrams for the different cell values, for these many cell values, 10, 11, 16, 17, 31, 32, and for two possibilities of the iterations. So either the number of the iterations could be fixed, like in the study we took the value of k fixed as 80, or the value of k can vary also. So for the varying value of the k, we took this this value of k varying is the ceiling of n by 2 minus 1. So this is the proposed classification. So in this classification, wherever I include the rules enclosed with a solid box, it represents the strong level of the association. And whenever I enclose the rules within dotted box, it represents the moderate level of the association. And like this here, these rules are moderately associated. And whenever I enclose the rules within this how to pronounce this, within this line box, then it represents the weak level of the association. So in the category 1, all the rules are strongly associated. So therefore, the value of all the four parameters would remain the same for all the rules, and the value of the DTW parameter would be equals to 0. And here within the dotted box, like the rules 50, 58, 77, 122, 178, so the values of the four parameters would remain, there could be a slight variation in the values of the four parameters, but then the value of DTW parameter would remain as 0 only. And for the rules enclosed within the line box, like here 754 and 94, so the values, there could be a slight deviation in the values of the 4 matrix, and the value of the DTW would be less than or equals to 0.5. So this is the proposed classification. So in this proposed classification, so we have categorized the rules into 5 different categories. So these are the characteristics of the category 1, that all the rules of the category 1 are characterized by the 0 value of the DE, SCI and SCA values with the very high value of the SCO. The values have been listed here. And for these many rules, we found the same values of the 4 matrix, and moreover, the value of the DTW parameter was equals to 0. So this is a representative entropy time diagram, rather diagrams of the category 1 for the different values of n, 10, 11, 16, 17, 31, and 32. And for all the rules which are there in the category 1, we found the exact same diagrams. And as far as the category 2 is concerned, so here the bientropy values stabilizes. So initially they start with a high value, initial high, and then stabilizes afterwards. So there are rules which are having strong association in category 2, and there are rules which are having moderate and the weak association also. So all the rules which are having strong association among themselves in this category are categorized by the low to high D value, very high SCO values, and 0 to 1, 0 and 1 value of the SCI and SCF respectively. The values have been listed here. So like for these many rules, we found the same set of the values and the same set of the diagrams. So this is the diagram for the rules which are being strongly associated. And for the rules which are moderately or the weak associated, we should not forget that their DTW value is definitely less than or equals to 0.5. And in the category 3, so in this category, the entropy values fluctuate or result in a periodic behavior. From initial high or fluctuating entropy values, and all rules, strong and weak, of the category 3 are characterized by the low to high DE and very high SCO values, with low to medium SCI and SCF values. So values have been, these are the representative diagrams of the category 3. So in the category 3, again, we have rules which are strongly, and moreover, most of the rules in the category 3 are strongly associated. So if we compare their entropy time diagrams, so we will find the exact same entropy time diagrams for the rules which are enclosed, which are strongly associated and enclosed within a single box. So now so these are the values of the 4 matrix for the category 3 for the different rules which are strongly associated. Category 4, in this category, the values of the entropy exhibit the chaotic behavior with a smaller cell size, which stabilizes as the value of n increases. So initially we start with a chaotic behavior, but then it gradually stabilizes as we increase the value of the n. And this is an underlying assumption of this study also. And this is one of the limitations of this study, that we assume that the largest value of the n considered here is 32, and a pattern shall surely evolve if it exists for the value of n is equal to 32. And all the rules of the category 4 are characterized by the low to high DE and high SCO values with very low SCI and low to high SCF values. So these are the representative entropy time diagrams of the category 4. So as we increase the value of n, so initially we see a periodic behavior, but then gradually it stabilizes. So for all the rules which are strongly associated in the category 4, we observe the same diagrams. Category 5, rules in the category 5 exhibited the mixed behavior of the previous categories, and with the different values of the cell length, none of these rules showed a 0 value of the DTW analysis with any other rule. So here the value of the DTW came out to be greater than 0.5. So the remaining rules have been grouped in the category 5. So this is the category-wise variation of the 4 majors in the category 1. So these are the values of the 4 matrix. Similarly, the values have been listed here. for all the 5 categories, all the 5 proposed categories, and in the category 5, we observed the mixed values of these 4 metrics. The limitations of this study is that it is assumed that a pattern shall surely evolve for the largest value of the n considered here, n is equal to 32 if it exists. And all simulations and analysis in this study are made for the periodic boundary condition with the simple seed, that is single non-zero at the center of the lattice, even though we conducted the experiments for with the random seed also and the multiple experimentations for the random seed. But then here in this study, uh, we do have the concrete results for the simple seed scenario. And these are the conclusions and the future scope of this study. So this paper uses a combination of the notions taken from the information theory and machine learning to present an alternative grouping of the ECA rules. And this study proposes the use of the entropy time diagrams as a phenotype and 4 measures to capture the genotype to examine the ECA's behavior. And clustering entropy value sequences for the different ECAs leads to their classification in the same category with a different association level, could be strong, moderate, or weak. And since this study analyzes synchronous ECA with the periodic boundary condition, it shall be interesting. So this is a future scope of this study, and I'm also planning to extend this study on these 2 lines. That it shall be interesting to examine the impact of asynchronicity or the different boundary conditions as a future scope of this study. And using the random seed in the initial configurations shall also be investigated as an extended work of the current exposition. And I'm very much thankful to Professor Sukanta Das sir, who conducted because this study is the outcome of the project done in the Indian Summer School. So I'm grateful to him for his gracious support and the guidance. And I'm also grateful to Dr. Kamalika Bhattacharjee, who helped me to improve the quality of this manuscript. And these are the references. I'm open for the questions and suggestions to improve this study. Thank you very much.
Thank you, Professor Goyal, for the nice presentation. So from the audience, is there any question? Okay, so Professor Goyal, I have one question. So you just classify the 88 minimum ECA rules into 5 classes.
Yes, sir.
So I just want to know that for same type of classification, 88 minimum ECA rules are classified into 4 like classes by the Wolfram. So is there any similarity between this classification and that
Wolfram's
earliest?
classification.
Yeah.
Sir, we do observe some similarity and some dissimilarity because here the intuition behind this classification is to group the rules which have got the similar transformational capability within the same category. So the Wolfram's classification is more qualitative in nature. And here in this study, we are presenting a way to quantify the configurations with the help of the bientropy function. So we did observe some similarity and some dissimilarity, but then for the dissimilarity also, we do have the reasons that why certain rules are appearing in the different classes. So basically the difference in the entropy time diagrams.
Okay, so I want to thanks once again for the Professor Goyal for the nice presentation. Thank you, sir.
Thank you so much, sir. Should I stop sharing?
Yes. Our next presentation on isomorphism in cellular automata. Please, authors, come to the rise.
Hello. Shall I start now? Okay. Good afternoon, everyone. My name is Vicky Vikrant, and I'm pursuing PhD from National Institute of Technology, Tiruchirappalli. I welcome you all for my research presentation topic. The title is Isomorphism in Cellular Automata. I would like to thank my mentor Sukanya Mukherjee ma'am, which I had done this project in the summer school. And also I thank Kamalika Bhattacharjee ma'am. So basically what is isomorphism? Isomorphism deals with the structure preserving techniques that holds the bijective function in which when two graphs are having the same edges and vertices with the same degree known as isomorphism. But the major challenge of isomorphism in cellular automata, it is more complex to analyze, and computationally it's very difficult and it's very expensive. So we'll look into that. So isomorphism allows us to formally define and compare the structure of different cellular automata and knows some yeah, because where from where? Actually, I could not able to see the screen from. Hello, hello. It's fine, ma'am. Hello. We have to close this maybe. So getting started again to compare and classify the. Hello, hello. Off now? Hello. It's fine now. Okay. Slides. From current. From current. Hello. So it leads with the it leads to a more efficient and algorithm to better solution for the real life. Once you know about our target is to just study the problem of cellular automata and isomorphism in cellular automata. So since we are all working on the same domain, cellular automata, so no need to define this cellular automata. So basically what we will work on in this isomorphism, we'll took the null and periodic both boundary conditions. So we'll define that null boundary condition if our cell position is x minus 1 is equal to xn is equal to 0, then it will, we can say that this is a null boundary condition. Also we will define the periodic boundary condition as this. And basically in our system we will use this configuration transition diagram as a characterization tool to analyze the isomorphism in cellular automata. So basically what is a configuration transition diagram? It is shown like if we are taking a rule vector like here, so we can demonstrate that there exists some vertices and edges. So if you take an example of non-uniform cellular automata under null boundary condition, so if we construct the configuration transition diagram, it will looks like this. So how will identify the isomorphism in cellular automata? Basically, non-uniform cellular automata. So basically, if we take graph G1 and G2, if we compare with this, like let's take an example of R1 as 6, 2, 32, 90, 20, like that. We'll take another non-uniform cellular automata as 9, 142, 165, and 65. Will see that these are isomorphic to each other because there exists the same length cycle here and here, and also we can see these 3 length cycle and this self. We can say that these are isomorphic to each other. So now let's synthesize that how can we construct or extract more cellular automata that deals with the isomorphism. So basically, we told about that two CAs are isomorphic if we get this state transition diagram, also called configuration transition diagram, have the similar structure. So it also exists this property equivalence relation. That equivalence relation tells about us that it is reflexive, symmetric, and transitive. So it is equivalence. So using we have two methods to synthesize our CA. First is to exchange to exchange the state of the cell, and second is to state the mapping of the cell. So we'll discuss one by one. So let's take an example again. Echo is coming again. So let's take an example. Rule 3 and 119. These CAs are basically isomorphic to each other. Let's construct this using the state configuration transition diagram. We can see that this is the state transition diagram for rule 3. And again, we'll construct the state transition diagram for 119. We can see that these are isomorphic to each other. So let's synthesize this using state exchange method. So basically what we are doing, let's take two configuration like we have took in the previous slide, that x1 and y, x and y in an n cell binary CA. So for that sets, we will see that using this equivalence relation, we can see that there is a relation between relation of this. So since they are bijective mapping, so we can say that these are if we construct that, then we can say that this f and f pi, if you are doing some bijective mapping, then we can say that these are isomorphic to each other with this with the different size neighborhood. And also let's take an example of a state exchange, which is basically we are going to develop this concept by exchanging this 2 3 and 3 2 position. Like we are taking 4 neighborhood 4 cell length CA ABCD. We will just exchange this CD to DC. So we'll see that the current configuration and next configuration, how they are behaving. So in this first configuration, we'll see that 0 is this current configuration will move to the 15. And again, if we are just exchanging this last 2 bit position with 0 0 and 1 1, we can see that in ABDC will DC changed like 0 0 0 0. There is no difference in this configuration. Now again, let's see in this configuration 0 1, we can see that it is exchanged to 0 0 1 0, and then this configuration has been changed. So like this, we will just exchanging this state. So based on that technique, we'll get the isomorphic CA. So like this, if you are doing this state configuration transition diagram, if you want to draw, then we can see that these are the isomorphic to each other. So we can see that these CAs having the same cycle length and same vertices, same edges, and same cycle length and same degree also. So we can say that these are isomorphic to each other. Let's take an example of non-uniform cellular automata under the periodic boundary condition. So we'll see, we will construct again that using the state transition diagram, that current configuration to the next configuration. We again draw this diagram. So we'll find out that these are again isomorphic to each other. These are again isomorphic to each other. We can see that. But here is the problem of the neighborhood. If we are constructing using the permutation, is also called the permutation method. So if we are constructing this CA, it has some problem with the neighborhood. We can see that there is 3 neighborhood we have taken, and we have taken in the 4 neighborhood with this isomorphic rules. Now fine. So our second method is state map. Basically, we are doing the complementation of the hello, it's fine now. Okay, so again we have just complementing the configuration. So by taking the example, we can see that quickly we have we can see that in ABCD, we just flipping this B position cell. So let's take an example, and I'll demonstrate using this example. So in the first configuration, if you're checking this 0, 0, just flipping this bit, this second position bit, will get 0, 1, 0, 0. So again, the transition will be changed. Like this, we'll construct again. So with this technique, we can flip all these bits one by one, and we'll get the isomorphic CAs. So here is the diagram of that, and we can see that these CAs are again isomorphic to each other. These 2 techniques that can extract the isomorphic CAs. Again, we have taken one example to demonstrate that a non-uniform cellular automata like 150, 32, 240, 41, 117, like this, if we are doing the state map again, just complementing the second bit position. So we again get this diagram, which having the same isomorphic diagram. So with these two techniques, we found out we can extract lots of we can extract so many isomorphic using these both techniques. So I got some experimental result from this technique. So here we can see that isomorphic cellular automata using the state map method. So here is the uniform CAs, and this is a non-uniform CS with the 4 cell length. And we also compare with the Lopez classification, that is based, this Lopez classification only deals with the uniform CAs. So we'll just check it out with the periodic boundary condition, and we'll check it out that these are isomorphic or not. We have this result. So again, we also do the permutation method, that is state exchange method. We'll get this isomorphic result. If you are checking for the 4 length CA, we'll get the 24 isomorphic results. So here also, again, we have compared with the different length of the CAs. So we'll get this result. So here the conclusion that we propose is the two strategies that determine the set of the cellular automata that are isomorphic to each other, and their permutation is found out that the d factorial to the power n minus 1 isomorphic, and also we talked about that while exchanging the state we will get the isomorphics here, but there is a larger neighborhood difference. So our future work will found the exact count of the partition on the given CA size, and the real life application is the cryptography. We'll look into that also. I will. I'd like to thank Professor Sukantu sir for his great valuable suggestions, supports, and also my mentor Sukanya Mukherjee ma'am and my supervisor Dr. Kamalika Bhattacharjee ma'am. So I'd like to thank. Here are some references. So I also got some experimental result over from this state map. So while increasing the number of length, comparatively the complexity also increases. The complexity will go in the worst case to the power n. So like this, we are getting, if we are increasing the cell length with the neighborhood under the periodic boundary condition, we will get the different. Thank you.
Thank you, Vicky, for the nice presentation. So, is there any question from the audience? So, Vicky, you are just showing that example for four states here. So, have you checked with others like state more than 4?
These are the results. These are the results. These are different neighborhood results.
This is for four.
Yes, sir.
5
cell length with the 3 neighborhood.
Okay. So, how like up to how much? Like how many cells you check?
Sir, actually the complexity becomes more. So I just checked with the n is equal to 8.
N equals to 8. Yeah. Okay. So that time it's the complexity is?
Complexity is around, in worst case, is goes up till to the power n exponential.
Okay. So that means
it's very
beyond
difficult.
Beyond it's like 8 cell, it's like very difficult to find this.
Yes, sir.
Okay. Yeah. Yeah. This online question. Okay. So. Yeah. So, Professor Goyal asking about what could be the interpretation of having two isomorsism CS. Question.
Sir, basically, we are just trying to analyze the complexity between these two non-uniform CAs. Already, uniform CAs, isomorphism in uniform CAs has been already done by the Lopez sir. So, the interpretation is like we will, in the real life kind of scenario, we'll compare the two complex behaviors using the cellular automata. We can see in the future.
I hope Professor Goyal is clear to you. Is there any doubt? Okay. Thank you. Okay, thank you, sir. So thank you, Vicky. Anyone? Any other question? Okay.
Thank you, sir. Thank you, sir.
Okay, our next presentation is online. So it's presentation on a cellular automata model for language shift in Algeria. So Professor Rezki.
Hi.
Yeah. So over to you, sir.
Do you hear me?
Hello, am I audible, sir?
Yes, I can hear you. Do you hear me?
Yeah.
Okay. So may I share my screen?
Just yes, sir, yes. Now you can share.
Do you see it now?
Yeah. Yeah, sir, visible.
Okay. Okay, so hello everyone. I want to thank the organizers not only for the conference, but for the summer school of last year. It was a good opportunity to develop this work, although I didn't develop it during the school, but the school was really helpful to start working in this direction. So I'm Rezki Chemlal from
Sorry,
Rusia
sir, for the
University.
interruption. Can you make it large screen, sir? Full screen? PPT?
Okay, okay. Is it better like that?
Yes, sir, it's fine.
Okay. I was just saying that I'm used to work on not models, but properties of cellular automata from dynamical systems and ergodic theory point of view. I'm still working in that direction, but I was interested in working at least one time on a model, and the model that based on another interest of mine, which is social sciences. So let's start with social studies perspective of languages in Algeria. Algeria is considered by sociologists as a multilingual country. This is the case of many African countries when we have different mother language and we have to embrace another language. So in the case of Algeria, we have French, which was, you know that Algeria was a French colony. So French is a dominant language. It's perceived as dominant language because it's still used in scientific and economic spheres. They use French instead of Arabic. In Algeria, we have another category, which are original population of Algeria, called Amazigh or Berber, which is deviation of barbarian, Roman word. This is the mother language of sometimes we say 25% to 40% of Algerian population. It depends on who do the statistics, because there is a lot of ideology behind these statistics. But let's say at least 25% of Algerian do not have Arabic. It's also my case as their mother language. So you have to choose. This is the case in Africa in general. You have to learn another language, which is not your mother language, because it's useful in economy, in science. This is the idea. This is a map of in dark gray regions in Algeria. So this is a map of Algeria. In dark gray, you have regions. I'm sorry, it's not really clear, but you have in dark gray regions that are mostly Amazigh regions. So here you have the mother language, which is dominantly Amazigh language. Okay, our model is a cellular automaton. I think I will skip the slides about definitions. I was following all the talks. I think the audience is familiar with the definitions of what is a cellular automaton in dimension D. I want just to mention that the model is in 2 dimensions and we are using the Moore neighborhood in our model. Okay, so how to model language shift? Recently in Algeria, there is a big debate about shifting from French to English, and the government decided last year is making movements to adopt English instead of French as the dominant language. So in this model, we want to predict how evolution of the languages uses in Algeria. So in our model, we will take people, they can speak as first language, it may be Amazigh or Arabic, and as second language, it may be French or it may be English. And each individual will decide to shift from a language to another one. You have in the first situation, Amazigh speaking couples may have kids born in towns when Amazigh is not dominant. So their kids may embrace Arabic as language instead of Amazigh. And you have the same situation with French and English. You have people deciding to leave French and switch or shift to English language. So in our model, we will have, we distinguish in our model 4 situations. So in state 00, you say that person speak Algerian Arabic and uses a second language English. And in state 01, person speak Algerian Arabic and uses a second language French. So just notice that 0 positioned to the left means that you speak Algerian Arabic, and 1 positioned to the left means that you speak Amazigh instead. And the second situation is, what is your secondary language? Is it French or English? So if we position 0 to the right, this means you speak English. So look here, state 00, your first language is Algerian Arabic and the second one is English. If you take state 10, so this, your first language is Amazigh and your second language is English. And if we position 1 to the right, this means that you have a second language, French. So to our model, we need just to give these states, to associate to the states numbers. So each state, Mn is associated with a number. You can see it's a somewhat development in base 2. So state 00 will be encoded as 0, state 01 will be encoded as 1, 10 as 2, and 11 as 3. It's just 1 to 2 power 1 plus 1 to power 0. Okay. And now, if a person will shift from a language to another language, this is the result of some kind of a social pressure from its neighborhood. This is why it's interesting to use a cellular automaton to model this, because it's usually a social pressure from your immediate neighborhood that will motivate the decision to change or to shift from a language to another language. So next question is how to measure this social pressure from your neighborhood. Okay. So we decided to create some kind of a majority rule, but that is going into 2 directions. So you will check in your neighborhood people that are speaking Amazigh, and perhaps this will motivate you to keep your Amazigh language. And you will check in your neighborhood people speaking English, and perhaps this will motivate you to abandon French and to go to English. This is the way, I mean, it's a majority rule, but working in at 2 levels in the same time. Okay, I will skip this ugly mathematical formulas and we'll go directly to the slide about an example. Here is an example. So we'll try to update to explain the state of this cell in the center. So it's encoded as 2. I put up the table again here just to remind what is 2. It's 1011. And if you want to measure the social pressure, it's just this cell will take its neighborhood and will check what is their first language. Is it Arabic or is it Amazigh? So you take just the sum of coefficients that are related to the first language. So if the states is 0, 1, 2, and 3, there is no 0 here. Just for example, for 3, it's 1, 1. So to the left, people are using Amazigh. So you have 1 person using Amazigh here. Okay. If you take to the state 2, also they are using Amazigh. So in the neighborhood of this cell, there is 2 persons using Amazigh, and the sum is 3. If you take the state, for example, of the use of English, we say that you will look to the right state, and here we have 1, 2, 3, 4, 5 ones, and the sum of English-speaking language in the neighborhood is 3. So this is the idea. You are using a kind of majority rule, but at 2 levels in the same time. I was trying to explain this instead of giving you, so this is the formula. If you have the sum related to people speaking Amazigh language, we have two parameters, so PZ for Amazigh and PE for English. So the first parameter, if your cellular automaton, if your sum in the neighborhood is bigger than this parameter, you will maintain Amazigh language. And also, if it is bigger than the second parameter, you will shift to English. This is the idea of how our cellular automaton works. Now, we studied the dynamical behavior of this model. And here, perhaps, I should give some basic definition. A dynamical systems is a couple, compact metric space. Usually, it's not necessary to be that, but usually it's a compact metric space. And you need a self-continuous map. We say that we have a periodic point if after some iteration of f, you will find again your initial point x. The basic element here is a fixed point when you have f of x is equal to x. We say that the point is an equicontinuity point, or some people say it's Lyapunov stable. And instead of this mathematical definition, I can show you this. So if you have your point x, is an equicontinuous point. So if you start near your point, so your iteration will stay in some kind of a ball. So you stay always near. This is the idea. This is all what I will need, I think, to study the dynamical behavior of a model. If you take the last definition about equicontinuity points and you try to apply them to cellular automata, you have the concept of a blocking word. When you are in a dimension one, a blocking word is a word when you put it in space of configurations, this prevents information from, I'm sorry, this is not a good way to explain it. If you have a blocking word and you change to the left or to the right, this will not influence the behavior of your space-time diagram. This is a way to have an intuition about that. And in dimension one, if you have a blocking word, this is equivalent to have an equicontinuity point. However, this is not true when you go to a higher dimension. And in higher dimension, the work in dimension one was done by Kurka, and in higher dimension, Gumber done some equivalent work when she defined what we can call fully blocking pattern and blocking pattern. There is some changes in higher dimension. And the idea, if you have a fully blocking pattern, you have equicontinuity point, but you do not have the equivalence anymore. Okay. So when we study dynamical behavior of our model, so it depends from two parameters, P-Z and P-E for English. So you can find initial investigation, you can find that the configuration 3 repeated to infinity is a fixed point. It's independent from all values of PZ and PE. And for values of PZ or PE less than 5 in general, we observe it through computation, a quick convergence to a simple fixed point of this form. For values PZPE equal to 99, all initial random configuration generated by computer tested were fixed point. However, when you do simulation on the computer, it may suggest that all points are fixed points, but this was just the way that our program generated a random configuration. But when you work it a little bit, you can find counterexamples that are not all points are fixed points. And this is a simple one. If you put some kind of square in the middle and you put 0 outside, the result is a configuration with square of 2's. So this is the definition, centered at position KK, and all remaining cells will be filled by zeros. And you can do little computation here and show it's not fixed point. So even if computer simulation suggested that all points were fixed points, this is not true for all points. Okay, At second stage, we try to find basin of attraction of fixed points. And here we devised something like play. I don't know if the audience is familiar with Minesweeper, because one of my students told me she do not know what is Minesweeper game, but this is a game you can find of your older version of Windows. It was coming with Windows, and playing Minesweeper, you need some. You need a part of initial guess and you need a part of algorithmics to play a really good Minesweeper game. So we found when we were trying to study basin of attraction of fixed points here, we find it was like playing a Minesweeper game. I can give you some examples. If you want to find what is the basin of attraction of fixed point 3 to infinity. So you have to figure out if I have a 3 here, what I should put in the iteration before, what I should put here, what I should fill in here to have at next stage 3. And you have here possible guesses for different values of parameters. So we are developing a computer program that will fill. It's not ready by now, but it's almost done. We are working on a program that will give you basin of attraction. This is our motivation, is to have a tool that is similar. I don't know how much you are familiar with dynamical systems, but there is some tools in dynamical systems to find attractors, basin of attraction of fixed points. For dynamical systems, on the interval, on compact parts of R to N. So we are trying to have an equivalent tool for cellular automata. This is the idea behind this work. Okay, we found some theoretical results, and for example, for basin of attraction of fixed points, if you have PZ and PE equal to 1, 1, the basin of attraction of the fixed point contains the cylinder 3, and for PZ and PE equal 9, 9 do not contain any cylinder. For the case PZ PE equal 1, 1, it's an elementary computation. For the case PZ PE, we use contradiction, and we can show that suppose any cylinder is in the basin of attraction, and you can construct a configuration that is in the cylinder, but cannot, when n goes to infinity, that cannot goes to your configuration. Okay, some perspective here. From a modeling point of view, we think that it's interesting to develop a language shift model using partition cellular automata. Because when you look to the map of Algeria, you cannot fix the parameters with the same values for each region, because you have regions in Algeria when there is a social pressure to maintain Amazigh language, for example, and you have regions when Amazigh are really a minority and the social pressure is really almost inexistent to maintain Amazigh language. You have also the French, which is really dynamic in some major cities through culture, through art. So you cannot say this is the best parameters or found best parameters to the whole Algeria. So you have to give specific values for each region. So we think that a future direction of this work would be to devise a cellular automaton for each region with different parameters and work on that. Okay, this is present you some references, and thank you.
Thank you. Thank you, Professor Rezki, for the nice presentation. So is there any questions from audience? Okay, so one questions from Professor Goyal, that is, what is
What if the social pressure is modeled as?
Yeah, it's in the chat box. So yeah, what if the social pressure is modeled as a heterogeneous quantity, like English speaking neighbors might insert more pressure in certain region? In what way it could affect equilibrium or convergence? Anyway, very interesting study. So, sir, over to Professor Rajus.
Okay, thank you for the question, but the point is, this is what is motivating our idea to work on a partitional cellular automaton, because if you consider, even at the town level in Algeria, do you hear me?
Yes, audible, Dr.
Okay.
Raj.
So if you take in the case of Algeria, you have regions that are where there is, even if you take it at the town or city level, you have cities when you could say that French is really dynamic and there is some kind of soft pressure to maintain French and not to go to English. But you have other cities with other sociological parameters that want to go to English. And this is the idea that we developed a tool, but this tool we cannot use it in a homogeneous manner for the whole country. Say, this is why we came with the idea, the conclusion with the idea that perhaps this cellular automaton may be used, but in a partitioned way. So we have to give different parameters for each region in Algeria.
Okay, thank you, sir. Thank you for the nice presentation once again. So now our next presentation is so another work. Its presentation is given by Tarun Kumar. So, hello, am I audible?
Yes, sir. Hello.
Yeah. So over to you. You can share your screen and
Yeah, sure.
Good morning, everyone. First of all, it's a pleasure to present our project topic in the ASCAT 2023 conference. And yeah, so my name is Deeraj, and I also have my batchmate here. I guess I'm audible.
Hello. Hi, you're audible.
Yeah.
Hello, Deeraj, you are not audible. Some. Yeah. Hello, Deeraj, you are not audible. So please check your audio. Please unmute yourself. Yes, hello, Tarun Kumar, please unmute yourself. Yeah. Okay, who is presenting? Yeah, Deeraj. I think Deeraj is presenting. Okay, so Deeraj, first you unmute yourself. You are not audible.
Yeah. So am I audible right now?
Yeah, you are audible now.
Yeah, fine. Sorry for the inconvenience. So yeah, my name is Deeraj, and I also have my batchmate here, Tarun Kumar. So we are currently pursuing our third year Metallurgy and Material Engineering Department in National Institute of Technology, Tiruchirappalli. So we are here to present on a project topic known as the Cellular Automata based simulation of intergranular fracture using hexagonal discretization. And we also have we have done this project under the guidance of our dear professor PG Kubendran Amos. So yeah, so the introduction. So more than two of us, I believe that everyone in the panel will be knowing about the cellular automata. But as a material scientist, we would like to give some insights about the materials and the structures, the properties, etc., etc. So yeah, so let's dive into the world of material science first of all, before going into a project. So first of all, there is something known as in material science. There is something known as the materials tetrahedron. So it consists of the four domains, that is the processing, structure, properties, and the performance. So yeah, so in this materials tetrahedron, we can take an example in the left hand side, that is the diamond structure and the graphite structure. So here it is a allotrope of carbon. We know that it is allotrope of carbon. Because of the difference in the structure, we could see a huge difference in their properties, such as graphite structure is used as a lubricant, whereas a diamond structure is used as a hard material where we can cut metals, etc., etc. On the contrary, in the right hand side, we could see that a food substance which is made by the same wheat or flour, but due to its different processing methods, we could say that the properties is like different from the two sweets that two sweet and the food that is mentioned here. So yeah, we in our main aim of the project is to correlate between the structure and its properties. So as a material engineer, I will be more focusing on the properties and its performance, and as a material scientist, I will be more focusing on structure and processing. So our project mainly characterizes between structure and properties. So the next slide. So the next thing is, so as a mechanical engineer, you could say that material is something that he sees through his naked eye. But when we come to in a material scientist, like he sees the material as a microstructure. So here the hierarchical order is given. So the starting is the component, and the second one that we can see through the naked eyes. The second one is the something that the microstructure that we are speaking here. This we could actually observe through the optical microscope. And the third, the substructure of this microstructure, it could be seen through the various electron microscopes. And furthermore down, we could also see the electronic structures in the substructures, which could be seen through the various spectroscopy such as NMR spectroscopy, etc., etc. So this is the hierarchical order. So we are going to more see in the microstructure and its properties. So the next we are going to see about the crystallinity. So yeah, so if you're going to take a material and if you're going to see in a crystalline solid, material is divided into two solids, the crystalline solid and amorphous solid. And in a crystalline solid, the atoms will be arranged in a more ordered manner, but in an amorphous solid, it will be arranged in a random manner. So this ordered manner actually we can say it is somewhat similar to the cellular automata. So so this is where the both cellular automata and the materials kind of have a correlation. So the next slide. Now we talk about the grains. So this we talked about the microstructure. So what is there in the microstructure are these grains. So in these grains, if you take a particular grain, we will be seeing that the atoms will be oriented in a particular direction and in a particular pattern in a single grain. So grain boundary is something where these there will be the different grains have different orientation. When these two meet at a point, when these two grains meet, there will be atoms which are either in the both of the both of the particular orientation. So they form as the grain boundaries. So so you could see the images where there is a formation of the grain boundaries. Next slide. So yeah, so here we have actually taken a classic example. The left side pictures the Titanic. So so we all know the reason for the failure of the Titanic is because it's because of the structure and the property relation. It's because so we all know the steel. So the steel doesn't behave as good as in the room temperature when it is in the cold temperature. So there is a so this was the misinterpretation made by the engineers those days. So so because of this, you could see like in the left hand side in the orange color structure. So here there is a ductile fracture made through. So and in the green structure we could see and something between ductile and brittle fracture, and in the blue structure we could see it is a complete brittle fracture. So this complete brittle fracture which caused the failure for this Titanic. So this fracture, so the next slide, we could see there's the intragranular fracture. So so I talked about the Titanic fracture. So like in that, we could say that it undergoed intergranular fracture because it is because like the basic, like there are two types of fracture actually, intergranular fracture and the transgranular fracture. So in intergranular fracture, the crack is propagated through the grain boundaries, whereas in transgranular fracture the crack is propagated through the grains. So this is the basic difference. So why does the intergranular fracture happens? It is because like maybe the processing route that we talked earlier in the material tetrahedron, that there could be improper processing route for the material. And the second thing, maybe in a specific environment, for example the Titanic case, this could happen where the grain boundaries are weakened, and thus if a force is applied, the grain boundaries are weakened, so thus the crack propagates along the grain boundaries. So now the model description will be explained by Tarun Kumar.
Yes. Am I audible? Yeah, hello. Hello. Hello, am I audible?
Hello,
Yeah, okay,
yeah,
thank
audible.
you. Yeah, so I'll continue on about the model. So Deeraj just talked about the materials aspect of it, which we felt was important to talk about at the start. And now we want to talk about like how we were able to model the structure using cellular automata. So one unique thing that we started off with was almost all cellular automata is done with a square or a conventional discretization, where your domain is discretized into say cells that are square, so or rectangular. And when you have rectangular or square cells, you will have, as shown here in this photo, you will have a neighborhood where there are 8 neighbors surrounding the cell in consideration. So what we have seen as engineers in a lot of different places is, especially in buildings and structures, hexagonal structures are used primarily because they have a much stronger they're much stronger and they're a better shape because they're ultimately made up of triangles. So we wanted to see if we could make a cellular automata and use a different type of discretization. So we used hexagonal cellular automata. We used a 19-state cellular automata. So one state was used to represent an uncrystallized state. So basically, it is not a part of any grain. And there were 18 other crystalline states. So these states, each state is represented by a different color in the final output, and each color represents a different grain orientation. So each grain is oriented in a particular direction in like a regular order, but each grain can vary from between each other. So that is shown by the different colors in our model. So I'll walk you through the model flowchart. So initially we just have a homogeneous domain that is completely just gray, and then we introduce nuclei for the grain to grow. So usually when you're cooling say liquid metal, when you're cooling it below the the melting point, certain nuclei will get introduced into the liquid, and these will start growing as you start cooling the material further. And these grains will grow and continue growing. So depending on the factors that you have, you will get different grain sizes, different grain shapes, and so on. So in our model, we are trying to simulate that. So we'll have grain growth. And finally, the grain growth will stop when you have the entire domain is filled with at least every cell in the domain has some certain value assigned to it. So you will have a polycrystalline microstructure. So following this, once we detect that we have a complete microstructure that we have generated, we start to identify which cells are along the grain boundary. So, and I'll have a few examples here and I'll walk you through them. So the generation of the microstructure starts like this. So we have a 50 by 50 domain here. So the reason we're using 50 by 50 is because it's a little bit computationally intensive to have this many different states. but we can always expand this into a larger if you want more fine details and resolution. So once you introduce different nuclei and you allow it to expand according to our rules, you will have nuclei that start to grow. And when the nuclei comes into contact with another nuclei, they stop expanding in that direction. And ultimately, you get a polycrystalline microstructure, which is very similar to what you can observe in the real life when you look under an optical microscope.
Hello. Hello, Tarun.
Yes.
Sorry for the interrupt. Try to finish by 5 minutes. Okay.
Yeah, sure, sir. So here, what I'm doing here is, this is an example. This is done with square discretization. So we have three different colors on the left here, and each color represents a different grain of different grain orientation. So once you have this microstructure, you're trying to identify which grains are on the boundary. So the model identifies which grains are on the boundary, and here to just represent that which ones are on the boundary, I mark them in green. And then there's a crack initiation. So from any one of those cells on the previous slide which are on the boundary, the green cells, a random cell is picked which is along the edge of the domain, and the fracture is initiated there. The fracture usually starts at the surface of the material, so it started at the edge of the domain here. And its neighboring cells, the neighboring cells to the last fracture cell is kept track of. And with this method, you are able to continue propagating the crack along the grain boundaries exclusively. So in the next step, you will have more cells that are fractured, which is indicated by the gray. And this further continues. And here you can see that on the left side, once a grain, the fracture that is indicated in gray reaches a point where there are three different colors or three different grains reaching, it has to pick one path to go along. Like it has to either continue along the orange or yellow path, or it has to go around the orange or blue path. Now, in material science, we have found that there's a lot of research that's done on this, and this depends primarily on the difference in the grain orientation. So, if the orientation between the two grains is very close, then the energy required to crack for the crack to propagate along the side is much less, and hence the crack will propagate along that because it's thermodynamically more favorable. So assuming in this case that the orange and the yellow has a lower difference in grain orientation, the crack will propagate like that, and you will have a complete crack. So apart from the crack just propagating, another thing that you see in real life is once the crack propagates, you also start to see that the crack starts to widen. So if you look at a sample, you will see a V shape, a wedge shaped basically. So to model that, we have a crack widening algorithm also implemented. So basically, every 4 evolutions of the crack propagation cycle, there'll be one cycle of crack widening that happens. So we have tested and tried with other ratios, but we feel that for every 4 cycles, it seems to work out and it seems to correspond well with other traditional results. So we have also compared how the microstructure looks when you have a conventional square cells versus hexagonal cells, and we saw that the conventional square cells give you more jagged outputs, whereas hexagonal gives you more smooth grain boundaries and edges. And this is another example of intergranular fracture where you can see the crack is widening as it propagates, and you get a typical wedge shape. And another very interesting application of this model outside the domain of material science is when you have a junction of more than one grain boundary, the model is able to choose one path and follow it. So if you're able to change the condition which the path is chosen, if you're able to just change that condition, you can use this model to basically find paths across different regions. And this cellular automata can be applied to say maps and where you want to find a path, say through mountainous terrain or something like that. So the potential for this model to be applied outside material science is also quite interesting. So finally, coming to the conclusion, we were able to efficiently model the morphology, so how the structure looks for intergranular fracture in polycrystalline systems. And the advantages of this compared to say molecular dynamic simulations is that this is very computationally efficient, and you're able to get very similar qualitative results. And there are also applications outside the materials domain, which we want to further look into. And finally, we would like to give our sincere thanks to Dr. Sukanya Das and Dr. Kamalika Bhattacharjee, ma'am, for just organizing the summer school that we participated in last year. It was really insightful, and also for giving us the opportunity to present our work at this conference. So thank you very much.
Thank you, Tarun, and thank you, Deeraj, for the nice talk. So from the audience, is there any question? Okay, so it seems to be no questions. So, okay, thank you once again for Tarun and Deeraj for the presentation. Thank you.
Now we hello. Now we request Dr. Shukanto Das to present our session chair with a small gift from our side. Thank you everyone. With this, we are winding up technical sessions of second day of ASCAT 2023. We have organized a small cultural program to rejuvenate your mind after this long technical talk-filled day. Professor Shoktinath Jha will be presenting an interesting talk and Dr. Monira Islam Papu will be performing Baul. To experience such program, we request both our virtual and physical mode participants to join us at 6:30 p.m. Thank you for joining once again.